Okay, today we're going to talk about a very interesting algorithm called Quicksort. Which was invented by Tony Hoare in 1962. Okay? And it has ended up being a really interesting algorithm from many points of view. And because of that, it turns out today's lecture is going to be both hard and fast. Okay, so everybody, if you see the person next to you sleeping, you'll want to say, let's get going. So it's a divide and conquer algorithm. And it sorts, as they say, in place, meaning that it just rearranges the elements where they are. So that's like insertion sort rearranges elements where they are. Merge sort does not. Merge sort requires extra storage in order to do the merge operation. Okay? To merge in linear time in place, it doesn't merge in place in linear time. It doesn't do it just by rearranging. So it's nice because it's in place, so that means that it's fairly efficient in its use of storage. And it also happens to be very practical. Okay, if you tune it a bit. Okay, the basic algorithm turns out if you just implement that, it's not necessarily that efficient, but if what you do is then do the standard kinds of things you do to goose up the runtime of something, and we'll talk a little bit about what those things are, then it can be very, very practical. So it uses divide and conquer paradigm. And so first step is divide. And to do this, basically it does it by partitioning. So it partitions the array, the input array, into two subarrays around an element we call the pivot, such that elements in the lower subarray are less than or equal to x, or less than or equal to elements in the upper subarray. So if we draw a picture, of the input array, so this partition step basically takes some element x, and everything over here is less than or equal to x after the partition step, and everything over here is greater than or equal to x. Okay? And so now the conquer step is pretty easy. You just recursively sort the two subarrays. So I recursively sort the elements less than or equal to x. I recursively sort the elements greater than or equal to x. Okay? And then combine is then just trivial, because once I've sorted the things less than or equal to x and sorted the things greater than or equal to x, the whole thing is sorted. Okay, so there's nothing to do really for the combine. So the key step in Quicksort is this partition step. So that's the thing that that does all of the work. And so you can view Quicksort as just recursive partitioning. That's all it is. Okay, just as merge sort was recursive merging, Okay, Quicksort sort of goes the other way around and does recursive partitioning. So the key is the linear time, by which I mean theta n, subroutine. And here's some pseudocode for it. This is actually slightly different from the book. So the book has one. In fact, there's a nice problem in the book that has even a different one. Okay, so, but they're all basically the same idea. This is partition A, P, Q. And what we're looking at this step of the recursion is the subarray A from P to Q. And basically, we pick a pivot, which we're going to just pick as the first element of the array, A of P. And the book, just for your information, uses A of Q. But I use A of P. Doesn't really matter. Okay? And then we set an index to P, and then we have a loop. Okay, so this is the code. So it's basically the structure of it is a for loop with an if statement in the middle. Okay? And so the structure of the algorithm of this partitioning step looks as follows. We set the pivot to be the first element. So here's P, and here's Q. Okay, so this is going to be our invariant for the loop. Okay, and at any time during the execution of a loop, I essentially have some values up to I, which are already less than or equal to x, and then some values that end at j minus 1 that are greater than or equal to x, and then I don't know about the rest. And so we start out with I equal to P and j equal to P plus 1. Starts out at P plus 1. Okay, so that everything is unknown except for x here. Okay? And then the idea is that it's going to preserve this invariant. And the way it does it is, as we go through the loop, is it looks at A of j, and it says, is it greater than or equal to x? Sorry, is it less than or equal to x? Okay, if it's greater than or equal to x, it does nothing. Okay, because what can happen? If this is greater than or equal to x, essentially it just goes to the next iteration of the loop, which moves this boundary, and the invariant is satisfied. Does everybody see that? Yep. Okay? But if it's less than or equal to x, I've got a problem. If I want to maintain the invariant, if this next element is less than or equal to x. And so what it does then is it says, oh, let me just move this boundary and swap this element here, which is greater than or equal to x, with this one here that's less than or equal to x, thereby increasing the size of this subarray, and then the invariant is satisfied again. Okay? It's a fairly simple algorithm. And it's actually a very tight and easy algorithm, so that's one reason that this is such a great piece of code. Okay? Because it's very efficient. Okay? Now in principle, so this basically, the running time for this on n elements is order n. Okay? Because I'm basically just going through the n elements and just doing a constant amount of work. And then just a constant amount of work outside. So this is a clever piece of code. In fact, in principle, partition is easy, right? Okay, if I weren't worrying about doing it in place, it's really a pretty easy thing to do. I take an element, I just compare every other element with it. Throw one into one bin, one into the other. That's clearly linear time. Okay, but often what you find is that just because you can do it that way theoretically doesn't mean that that's going to end up giving you good code. And this is a nice piece of code that allows you to do it in place. Okay, and that's one reason why this is a particularly good algorithm, because the constants are good. Okay, so yes, when we do asymptotic analysis, we tend to ignore the constants, but when you're actually building code, you care about the constants. Okay? But first, you care much more than just about the constants, is whether overall it's going to be a fast algorithm. Okay, let's go through an example of this. Guess I'll do it over here, just so we get the gist. So here's a sample array that I've created out of whole cloth. Okay, and here we're going to set x, the pivot, to be 6. Okay, and so let's look to see how this algorithm works. So I starts out here, and j starts out here. Okay, if we initialize. And what we do is we start scanning right. Essentially, that code is scanning right until it gets something which is less than or equal to the pivot. So it keeps going here till it finds, j keeps incrementing until it finds something that's less than or equal to the pivot. And in that case, it's the number 5. And then it says, well, swap these two things. Okay, and it does that, and we get 6, 5, 13, 10, 8, 3, 2, 11. Okay, and meanwhile, now I gets incremented, and j continues where it left off. Okay, and so now we keep scanning right until we get to something that's less than or equal to the pivot. In this case, it's 3. So we swap 3 and 5, and we get 6, 3. Okay, and now at this step, we increment I, we start j out here, and in this case, right off the bat, we have something which is less than or equal to x. So we swap these two. Oops, I blew it, didn't I? Oops, what did I do? I swapped the wrong thing, didn't I, here? Aha! That's why I'm not a computer. Good. We should have swapped this guy, right? Swap I plus 1. Right? So this was I. We swap I plus 1. Good. So, that's all wrong. Let's swap the right things. So now we get 6, 5, 3, 10, 8, 13, 2, 11. That even corresponds to my notes for some strange reason. Okay? So this is I, and now this is j. Okay? And now when I look, I immediately have something that's less than or equal to the pivot. So we swap this and I plus 1. So now we have 6, 5, 3, 2, 8, 13, 10, 11. Okay, and we, at that point, increment I to here. And we have j now going here. and j runs to the end. Okay, and the loop terminates. When the loop terminates, there's one last swap that we do, which is to put our pivot element in the middle between the two subarrays. Okay, so here we swap this one and this one, and so that gives us then 2, 5, 3, 6, 8, 13, 10, 11, and this is the pivot, and everything over here is less than or equal to the pivot, and everything over here is greater than or equal to the pivot. Okay? Okay, so the quicksort routine, once we have this partition routine, quicksort is a pretty easy piece of code to write. Oh, I do. Ooh, I should have said return here I, right? Got to return what the pivot. Yeah, here I've got to return I, because we want to know where the pivot element is. Sorry, bug in my code. Okay, so R gets partition of A, P, Q, and then we quicksort A, P, R minus 1, and quicksort of A, R plus 1, Q. Okay? And that's it. That's the code. The initial call is quicksort of A, 1, N. Okay? Because once we've partitioned, we just have to quicksort the two portions, the left and right portions. So just the boundary case is probably worth mentioning for a second. Okay, so if there's 0 or 1 elements, that's basically what can possibly happen here, is that I get 0 or 1 elements here. Then the point is there's nothing to do because the array is sorted, either because it's an empty array or because it only has 1 element. One of the tricks to making quicksort go fast as one tunes this is to, in fact, look at having a special purpose sorting routine for small numbers of elements. So, for example, if you get down to 5 elements, having some straight line piece of code that knows how to sort 5 elements efficiently, as opposed to continuing to go through recursion in order to accomplish that. And there are a variety of other things. This is a tail recursive code, and so you can use certain tail recursion optimizations. And there are a variety of other kinds of optimizations that you can use to make this code go fast. So yeah, you can tune it up a bit beyond what's there, but the core of it is this efficient partitioning routine. Okay. So, that's the algorithm. Turns out that looking at how fast it runs is actually a little bit challenging. Okay? So in the analysis, we're going to assume that all elements are distinct. Okay? It turns out that this particular code does not work very well when you have repeated elements. But Hoare's original partitioning routine is actually more efficient in that case if there are duplicates, okay, in what you're sorting. And I encourage you to look at that, but it's got a more complicated invariant for partitioning routine, but it does a similar kind of thing. It's just a bit more complicated. Okay. If they weren't all distinct, there are things you can do to make them distinct, or you can just use this code, but the easiest thing to do is just use Hoare's original code, because that works pretty well when they're non-distinct. Okay, but this is a little bit easier to understand. So let's let T of n be the worst case running time on n elements. Okay, and so what is the worst case? What's the worst case going to be for Quicksort? Yeah.
You always choose a pivot where everything is greater than or less than?
Yeah, that's right. If you always pick the pivot and everything is greater than or everything is less than, you're not going to partition the array very well. And when does that happen? What's the original input look like that makes that happen?
It's already sorted.
Yeah, if it's already sorted or reverse sorted. Okay, so if the input is sorted, or reverse sorted. That's actually kind of important to understand, because it turns out the most common thing to sort is something that's already sorted. Okay, surprisingly. Okay, or things that are nearly sorted. But often it's just, it's sorted, somebody wants to make sure it's sorted. Well, let's just sort it again rather than checking to see if it's sorted. Okay? And in those cases, one side of the partition, of each partition, has no elements. So then we can write out what the recursion is for that. So if T of n, if one side has no elements, we're going to have T of 0 on that side, and on the other side we're going to have T of n minus 1. So that we're just writing out the recursion for this. Okay? So one side has no elements, the other side has n minus 1 elements, and then the partitioning and all the bookkeeping and so forth is order n. Okay? So what is T of 0? What's T of 0? What is that asymptotically?
Constant.
Yeah, it's a constant, order 1. Okay? So that's just order 1 plus T of n minus 1 plus order n. Well, the order 1 can be absorbed into the order n, so this is really just saying it's T of n minus 1 plus order n. And what's that equal to? Yeah, that's order n squared. Okay, order n squared. Why is that order n squared? Yeah, it's an arithmetic series. Okay? Okay, actually just like we got for insertion sort. Just like for insertion sort. Okay, it's an arithmetic series. We went through all that work, and we have an algorithm called Quicksort, and it's no faster than insertion sort. Okay? Nevertheless, I said it's a good algorithm. Okay? The reason it's a good algorithm is because its average case time, as we're going to see, is very good. Okay? But let's try to understand this a little bit more, just so that we understand the difference between what's going to happen in the average case and what's going to happen in the worst case. So let's draw a recursion tree for this. For T of n equals T of 0 plus T of n minus 1 plus, and I'll make the constant explicit for Cn. Okay, so we get an intuition of what's going on. So some constant times n. And then we have T of n is equal to, and we write it with the constant part here, Cn, and then T of 0 here, and T of n minus 1 here. Now I know that all you folks are really fast and want to jump immediately to the full-blown tree, but let me tell you, my advice is that you spend just a couple minutes writing out. It only costs you, since the tree grows exponentially, it only costs you a constant overhead to write out the small cases, okay, and make sure that you've got the pattern that you're developing. So I'm going to go one more step. So here we have t of 0, and now this becomes this becomes c times n minus 1, and now we have another t of 0 over here, and t of n minus 2. And we continue that, until we get to, so that's all equal to Cn with a t of 0 here, c times n minus 1 with a t of 0 here, c of n minus 2, okay, t of 0 here. And that all the way goes down till we end up with order 1 down here. Okay? So, what's the height of this tree? What's the height of the tree here? Yeah, n. Good. Okay? Because every step, we're just decrementing the argument by 1. Okay, so the height is n. Okay, so to analyze this, let's first add up everything that's here. Okay, so this is just so we understand where these things are coming from, this is just theta of the summation of k equals 1 to n of k. Actually, of ck. Okay? So that's what's in there, and that's equal to order n squared. So that's where our arithmetic series is coming from. So that's order n squared. Okay? And then all these things here are all theta 1s. And how many of them are there? They're order n. Actually, there's n theta 1s. Okay? So the total amount ran out of space. The total amount, we'll just use it up here, is T of n equals theta of n plus theta of n squared, and that's just equal to theta of n squared. Okay? So just to see what the structure is in terms of the recursion tree. Okay? It's a highly unbalanced recursion tree. Now I'm going to do something that I told you you should never do, which is we're going to do a best case analysis. Okay? So this is for intuition only. And in general, we don't do best case analysis. It doesn't mean anything. Unless we get some intuition for it, maybe. But basically, it means nothing mathematically because it's providing no guarantee. Okay? And so this is intuition only. Okay? So if we're really lucky, what happens for partition? What's going to be the lucky case? Yeah, it splits, boom, right in the middle. Okay, which is essentially n over 2 to n over 2. It's really n over 2, n minus 1 over 2 to n minus 1 over 2, but we're not going to worry about the details because we're only doing intuition for the best case, because best case is not what we want. So if that happened, what's the recurrence that I get? Imagine it split it exactly in the middle every time. Then what happens? So you get T of n equals, you get 2 times T of n over 2, good, plus the order n time for partitioning and bookkeeping. And what's the solution of that recurrence? Yeah, that's n log n. That's the same as the merge sort recurrence. Okay, it's which case of the master theorem? Yeah, case 2. Right? Because n to the log base 2 of 2 is n to the 1. It's the same. So we tack on the extra log n. Okay? Case 2 of the master theorem. Okay? So that's pretty good. That says that in the best case, Quicksort's going to do well. How about, let's suppose the split is always, let's say, 1/10 to 9/10. Okay, 1/10 times n, 9/10 times n. Okay? Suppose it's always, okay, is that, in that case, are we lucky or are we unlucky? I mean, if the split is really skewed, we're clearly going to be unlucky. Right? Because then it's, say, 1 to n. If it's really in the middle, it's n log n. What do you suppose it is if it's 1/10 to 9/10? Is that lucky or unlucky? Who thinks, we'll have a little democracy here. Okay? Who thinks that that's a lucky case? Okay, you know there's going to be fast running time. And who thinks it's an unlucky case? Okay, so we have some brave soul. And who didn't vote? Oh, come on. Come on. Come on. It's always better, by the way, to say yes or no and be right or wrong, because then you have some emotional commitment to it and you'll remember better. Okay, rather than just sitting and being quiet. Okay, you don't manipulate your own emotions well enough to remember things well. So those people who voted win over the people who don't vote, whether they're right or wrong. Okay. So let's take a look. So here's the recurrence. T of n is equal to T of 1/10 n plus T of 9/10 n plus theta n, and we'll assume that this is this part here is less than or equal to some Cn. Okay, in order to analyze it. So we'll just do a recursion tree for this and see. So here's a recursion tree. So we have T of n. That's equal to Cn, T of 1/10 n, T of 9/10 n. Now we have, again, Cn at the top. Oh, this gets complicated, right? This is 1/10 Cn. And now over here we have 1/10, and then we're plugging it into the recursion again, so we now get T of 1/100th n. And over here we get T of, 9/100ths n. And over here we have now 9/10 Cn, and that gives us here T of, 9/100ths n again, and here we get T of 81/100ths n. Okay? And we keep going on. Okay? So that's equal to Hope we're going to be able to fit this. Cn, we have 1/10 Cn here. Down this way we have 1/100th Cn, and that keeps going down until we get to order 1 down here. And over here we have 9/10 Cn. And here, let's see, this is 9/100ths Cn, and this is now 9/100ths Cn, and this is 81/100ths Cn. And these things keep going down, okay, till they get down to order 1. But the leaves are not all at uniform depth here, right? I mean, this side is way further up than this side, right? Because here we're only going down by 9/10 each time. So in fact, what's the height looking, or what's the length of this path here? What's the length of this path down to this leaf if I take the leftmost spine? Somebody raise a hand? Yeah. Log base 10 of n. Okay, log base 10 of n. Okay, because I'm basically cutting down by a factor of 10 each time, and how long does it take me to reduce it to 1? That's the definition, if you will, of what a log is. Okay, log base 10. Okay, what's this one? What's this path going that way? Yeah.
Log base 10 over 9.
Yeah, log of n. Okay. Log base 10 over 9 n. Because we're going down by 9/10 each time. Okay, once again, essentially the definition of n. And everything in between there is somewhere between log base 10 of n and log base 10/9 of n. Okay? So everything is in between there. So now what I can do is do the trick that we did for merge sort in looking at what the evaluation of this is by adding up what's the cost of the top level. So that's just Cn. And what's the cost of the next level? Cn. And what's the cost of the next level? Cn. Okay? So every level we're still doing the same amount of work. Okay? And we take that all the way down. Okay? And the last levels, eventually we hit some point where it's not equal to Cn, where we start getting things that are less than or equal to Cn, because some of the leaves start dropping out. Okay? Starting at this level. Okay? But we keep getting, so we basically, this part is going to be log base 10n, and then we start getting things that are less than or equal to Cn. Okay? And so forth, until finally we get to add it all up. Okay? So T of n is going to be less than or equal to Cn times, well, what's the longest that this could possibly be? Log base 10 of n. Sorry, 10/9 n. Okay, plus we have all of the leaves that we have to add in. But all the leaves together add up to just order n. Okay? All the leaves add up to order n. So we have plus theta n. Okay? And so this is how much? If I add all this together, what is this asymptotically? That's n log n. Okay, so T of n is actually bounded by n log n. So we're lucky. Those people who guessed lucky were right. Okay? A 1/10 to 9/10 split is asymptotically as good as a 50-50 split. Okay? And in fact, we can lower bound this by just looking at these things here and discover that, in fact, T of n is lower bounded by Cn log base 10n plus order n. And so T of n is lower bounded by also asymptotically n log n. So T of n is actually theta of n log n. Now this is not really a proof. I generally recommend that you don't do this kind of thing to do a proof. This is a good intuition, recursion trees. The way you prove this is what? Substitution method. Good. Okay, so what you do is use this to get your guess, then use substitution method to prove that your guess is right. Because it's too easy to make mistakes with this method. Okay, it's very easy to make mistakes. With substitution method, okay, it's harder to make mistakes. Okay, because there's just algebra there that you're cranking through. So it's easier to verify rather than dots and trees that you drew improperly and wrote in wrong amounts and so forth. Okay? Okay? So this is n log n, so that's pretty good. So it's order n log n, and we're lucky. Okay. So now let's try another one. Suppose, this is all for intuition, because I'll tell you, by the time we get to the end of this class, you folks are going to be bolting for the door. Okay, because we're going to do some good math today, actually. It's actually fun math, I think, but it is challenging. So if you're not awake, you can still sleep now. I'll tell you when to wake up. Okay? So, one more bit of intuition. Suppose that we alternate steps. Suppose we do the partitioning thing, and it happens that we start out lucky, and then we have a partitioning step that's unlucky, and then we have a step that's lucky, and a step that's unlucky. We do that all the way down the tree. Okay, so suppose we alternate. Okay? So are we lucky or unlucky if we do that? Okay, so this time I want everybody voting. Doesn't matter what your answer is. Okay? Everybody has to have a stake in the game. Right? It's sort of like horse racing. If you ever watched horse racing, it's really boring. You put a little bit of money down. Okay? A little skin in the game. Okay? Suddenly it's interesting. Okay? So same thing here. Okay? So I want everybody with some skin in the game. So who thinks this is going to be lucky? Whoa. Who thinks it's going to be unlucky? Whoa. Okay. Who didn't vote? You guys. No skin in the game, huh? Okay, so let's analyze this. So we can once again write a recurrence. On the lucky step, we'll have L of n be the running time on a lucky step of size n. And that's going to be twice, well, the next step is going to be unlucky. So it's 2 unluckies over 2, plus order n. So that's our lucky step. And then for the unlucky step, we're going to have that is essentially going to be L of n minus 1. It's going to be lucky on the next step, plus order n. So that's unlucky. Okay? So see how I've described this behavior with a system now of recurrences, okay, that are dependent, where the boundary cases, once again, which aren't unstated, is that the recurrences have a constant solution, okay, with constant input. Okay? So, now we just do a little bit of algebra using substitution. L of n is then equal to, well, I can just plug in, for u of n over 2, plug in the value of u of n over 2. And that gives me 2 L of n over 2 minus 1 plus theta n plus theta n. Okay, so see what I did here? Okay, it's simply plugged in, for u of n over 2, I plugged in this recurrence. In fact, technically, I guess I should have said here theta of n over 2, just to make the substitution more straightforward. It's the same thing, but just to make it, not to skip a step. Okay? Not to skip a step. Okay, so that we can now crank through, and that's 2 L of n over 2 minus 1 plus, and now I have 2 theta n over 2's plus another 1. So all of that is just order n. And what's the solution to that recurrence? N log n. Okay? Theta n log n. Everybody see that? Okay? Theta n log n. So this is basically just, once again, master theorem with a little bit of jiggering here. Okay? That minus 1 is only going to help us, actually, in the solution of the master theorem. Okay? So it's order n log n. So we're lucky. So if we alternate lucky and unlucky, we're lucky. So how can we ensure that we're usually lucky? So if I have the input already sorted, I'm going to be unlucky. Okay? Excuse me? You could randomly arrange the elements. That's one way. Okay? That's one way. What's another way? That's a perfectly good way, actually. And in fact, it's a common thing to do. Yeah?
Randomly choose the pivot.
Randomly choose the pivot. Okay? Yeah, so it turns out those are effectively equivalent. Okay? But we're going to do the randomly choose the pivot because it's a little bit easier to analyze. Okay? But they're effectively equivalent. And so that gives us the algorithm called randomized quicksort. Okay? And the nice thing about randomized quicksort is that the running time is independent of the input ordering. Okay? Very much for the same reason that if I just scrambled the input, it would be independent of the input ordering. Right? If I randomly scramble the input, then it doesn't matter what the order of the input was. Whereas original quicksort has some slow cases, input sorted or reverse sorted, and some fast cases. Okay? In particular, it turns out that if it's random, it's going to be pretty fast. Okay? If I actually randomly scramble the input or pivot on a random element, okay, it doesn't matter what the input was. So if you were competing, one way to think about this is with an adversary. Okay? Imagine your adversary. You're saying, I have a good sorting algorithm. And he says, I have a good sorting algorithm, and you're trying to sell to a single customer. And the customer says, okay, you guys come up with benchmarks for each of your algorithms. And you get to look at his algorithm. Well, you look and you say, oh, he's using Quicksort. I'll just give him something that's already sorted. Okay, that's what you could do to him. If you had Quicksort, he would do the same thing to you. Okay, so how can you defeat him? Well, one way is with randomization. Okay, big idea in computer science. Okay, use random numbers. Okay, so the idea here is if I permute the ordering at random, as one suggestion, or I pivot at random places, okay, then the input ordering didn't matter. And so there's no bad ordering that he can provide that's going to make my code run slowly. Now, I might get unlucky, but that's just unlucky in my use of my random number generator. It's not unlucky with respect to what the input was. What the input was didn't matter. Everybody follow that? Okay? So the nice thing about randomized quicksort is that it makes no assumptions about the input distribution. You don't have to assume that that all inputs are equally likely, because either you can make it that way or you pivot in a way that makes that effectively hold. And there, in particular, there's no specific input that can elicit the worst case behavior. Okay? The worst case is determined only by a random. number generator. Okay? And therefore, since it's only determined by a random number generator, we can essentially bound the unluckiness mathematically. You can say, what are the odds? Okay? Okay, so we're going to analyze this. And this analysis is, this is where you know whether you belong in this course or not. If you skipped 6042 or whatever, this is a good place to do the comparison. Since it is going to be a little bit, why don't people just stand up for a moment and take a stretch break? Okay? Since this is going to be a nice piece of mathematics we're going to do, you're going to want to feel fresh for it. Okay. Stretch break is over. Okay, analysis. Good. I think we're going to make this. Okay. I'm sort of racing. There's a lot of stuff to cover today, so. Good. So let's let T of n now be the random variable for the running time. Okay, assuming well, I didn't even write here what we did here. So we're going to pivot on a random element. Okay, so that's the basic scheme we're going to do. And the way I do that, by the way, is just in the code for partition. Rather than partitioning on the first element, before I do the partition, I just swap the first element with some other element in the array, chosen at random, perhaps itself. So they're all equally likely to be pivoted on. And then just run the ordinary partition. Okay. So this is the random variable for running in time, assuming we have to make an assumption for doing probability. The random numbers are independent. Okay, so when I pivot in one place, it's independent of how I pivoted in some other place as I'm running this algorithm. Okay? So then, to analyze this, what I'm going to do is I want to know where we pivoted. So for k equals 0, 1, up to n minus 1, okay, let's let, for a particular partition, the random variable x sub k be 1 if partition generates a k to n minus k minus 1 split. Okay, and 0 otherwise. So I'm picking, in the partition routine, I'm picking a random element to pivot on. Okay? And x sub k is going to be my random variable that's 1 if it generates a split that has k elements on the left side and n minus k minus 1 elements on the right side of the pivot. Okay, sum of those two, of course, is n minus 1 because I also have the pivot. Okay? And 0 otherwise. So I now have n random variables that I've defined associated with a single partition. Okay, where all of them are going to be 0 except one of them, whichever one happens to occur. Okay, is going to have the value 1. So this is called, by the way, what's the name of this type of random variable? Bernoulli, or, well, Bernoulli has other assumptions. Okay, so, but, okay, it's an indicator random variable. Okay? Turns out it is Bernoulli, but that's okay. It's an indicator random variable. Okay, it just takes on the value 0, 1. And Bernoulli random variable is a particular type of indicator random variable, which it turns out these are. Okay? So that's an indicator random variable. Indicator random variables are a good way when you're trying to understand what the sum of a bunch of things is. It's a good way to break apart your big random variables into smaller ones that can be analyzed. Okay. So let's just take a look at this indicator random variable. What is the expectation of x sub k equal to? In other words, what is the probability that I generate a k to n minus k minus 1 split? So x sub k is, let's just write out what that means, okay, just to refresh people's memory. That's 0 times the probability that x sub k equals 0 plus 1 times the probability that x sub k equals 1. Okay? Which is equal to, well, that's all 0. That's just equal to the probability that x sub k equals 1. And that's a general property of indicator random variables, is that their expectation is that the probability that they're 1. So it directly connects, the nice thing about indicator random variables is it directly connects the probability to the expectation without any other terms going on. Okay? So what is the probability that x sub k equals 1? 1 over n. Okay? 1 over n. Okay? So all splits are equally likely. Okay? And I have n elements, so each one has a 1 over n chance of being picked as the pivot. And once you pick the pivot, that determines what's on the left and the right and so forth. Okay? So that's 1 over n. So everybody with me so far? Okay, more or less? Okay, as I say, this is going to test whether you're in the class. Okay, if you go home and you study this and you can't get it, then, and you have a deficiency in your math background in trying to take the course, this is a good indication that probably you've taken something a little over your head. Okay? Okay, so then T of n, so let's write out what T of n is equal to here. So, T of n is going to be equal to T of 0 plus T of n minus 1 plus theta of n if we get a 0 to n minus 1 split. Right? And it's equal to T of 1 plus T of 2, n minus 2 plus order n if we have a 1 to n minus 2 split. Okay? Okay, and now down here it's going to be T of n minus 1 plus T of 0 plus theta n if we end up with an n minus 1 to 0 split. Okay, so this is our recurrence for T of n. And unfortunately, this recurrence is kind of hairy because it's got n cases. And this is once again where the brilliance of being able to use indicator random variables comes in. Because we will be able to take this case analysis and reduce it to mathematics. Okay, so we don't have cases, okay, using indicator random variables. And the way we do that, okay, is using the following trick of converting the cases into a summation. Okay, so let's just take a look at why these two things are the same. Okay. So the indicator random variable is 0 except if you get the particular split. So therefore, this summation is going to be 0 except for that k which actually appeared, in which case it's the value that we say it is. Okay, see the trick? Using multiplication by a 0-1 variable to handle all the cases. Okay, I think that's damn clever. Okay, I think that's damn clever. Okay, and this is like the classic thing that you do with indicator random variables. One of the reasons they're very powerful method. Because now we actually have a mathematical expression, hairy although it may be, okay, for our recurrence. Okay? Now what we're going to analyze is the expected value of t of n. That's what we want to do. Okay, what's the expected value of t of n? So to do that, I just write the expected value of t of n is equal to the expected value of this big summation. And now we can go ahead and start to evaluate the expected value of that summation. Okay? Is everybody with me? Yes? Any questions at this point? I see a thumbs up. That's nice to see. But I generally believe that what I want to see is no thumbs down. Okay? Okay? So it's good to see the thumbs up, but that means one person understands or thinks he understands. Okay. Okay. So this is, I claim, equal to the following. Actually, I'm going to need a little space here, so I'm going to move the equal sign over a little bit. Okay, so I claim that summation is equal to that. This expectation is equal to that summation of expectations. Okay, so why is that? What are the magic words that justify this step? Linearity of expectation. Okay? The expectation of a sum is the sum of the expectations. Okay, so that's linearity of expectation. I don't need independence for that. That's just always true for any random variables, expectation of any random variables. Okay? The sum of the expectations is the expectation of the sum and vice versa. Okay. So here we did the vice versa. Okay. So that's equal to now the sum of k equals 0, n minus 1 of expectation of x sub k times the expectation of t of k So why is that true? So what I've done is I've said the expectation of the product is the product of the expectations. That's because of independence. So what's independent of what? Okay. The x sub k here, random variables, are independent of any of the other partitionings and the, if you will, the x sub k that would exist for any of the other recursive calls. Okay? So whatever happens in here is independent of what happened there. Okay, so we're actually hiding, since we have a recurrence, we're not partitioning the same way each time, we have a different one. So we actually have something going on underneath the mathematics you have to pay attention to that the mathematics alone isn't really showing, which is that in t of k there's actually a set of random choices that are being made, if you will. Okay? And so you have to understand that those are independent of those, in which case we can multiply the probabilities of their expectations. Okay, everybody with me? Okay, so that's a big one. Independence of x of k from other random choices. Okay, that's equal to, now, well, first of all, this is nice. What's expectation of x sub k? 1 over n. Okay, that actually doesn't even belong in the summation. We can just pop it outside. Okay, so I get 1 over n times the sum of k equals 0 to n minus 1 of expectation of t of k plus 1 over n summation k equals 0 to n minus 1 of expectation of t of n minus k minus 1 plus 1 over n summation k equals 0 to n minus 1 of the theta n. Okay? So that's once again using linearity of expectation there, this time to split up these pieces. And just factoring out the expectation of k as being 1 over n. Everybody with me still? Okay. Okay, so all of this is elementary. It's just it's one of these things that's hard just because there's so many steps. Okay? And it takes that you've seen some of this before. Okay, so now the next observation is that these two summations are in fact identical. They're the same summation, just in a different order. This is going T0, T1, T2, T3 up to T of n minus 1. This one is going T of n minus 1, T of n minus 2, T of n minus 3, down to T of 0. So these are in fact equal. So therefore I have two of them. And then what's this term equal to? What's that one equal to? Theta n. Okay? So let's just see why. So the summation of 0 to n of theta n is theta n squared divided by n. Or if I want to bring the theta n out, I have 1 times the summation of k equals 1 to n of theta 1, or of 1. So once again, I get n. Either way of doing it. Okay? Okay, so this is in some sense so this is because the summations have identical terms, and this is just algebra. Okay. So now what we're going to do is do something for technical convenience, because we're going to absorb the k equals 0 and 1 terms into the theta n for technical convenience. So we have a recurrence here where I have an order n. And if I look at the cases where k equals 0 or k equals 1, I know what the expectation is for 0 or 1. The expected cost is the worst case cost, most of the worst case cost, which is constant. Okay, because I'm only running it for, I'm only solving the problem for a constant size. And we know that for any of the boundary cases that our solution of recurrence, our assumption is that it's constant time. So I can basically just take those two terms out, and all that does is accumulate some more constant here in the theta n. It's going to make the solution of the recurrence a little bit easier. Okay? And if I do that, I get expectation of t of n is 2n summation k equals 2 to n minus 1 of expectation of t of k plus theta n. all of that work was to derive the recurrence. And now we have to solve it. Okay, so just to review what we did, okay, we started out with a recurrence which was for the random variable, which involved a case statement. We converted that into some mathematics without the case statement, just with a product, and then we derived a recurrence for the expectation. Okay, and now we're in the process of trying to solve that recurrence. So we've done some simplification of the recurrence so that we understand what it is that we're going to solve here. Okay? By the way, I don't give things like this on quizzes. I do expect you to understand it. The elements of this you will find on a quiz. You know, this is a lot of work to figure out. Okay? This took smart people to do. Okay? Even though it's all elementary. But working out something like this, the elementary level, is still a bit of work even for somebody who's knowledgeable in this area. So now we're going to solve that recurrence, that last recurrence over there. And we're going to prove that the expectation of t of n is less than or equal to a n log n for some constant a greater than 0. That's going to be what we're going to do. And so what technique do you think we should use to prove this? Does this look like a master method? It's nothing like the master method. Okay, so when in doubt, do substitution. Okay? It's the granddaddy of all methods. Okay? So what we'll do is solve the base case by simply choosing a big enough so that a n log n is bigger than the expectation of t of n. Okay? For sufficiently large small n. Okay, so I just pick A to be big enough. And this is, by the way, why I wanted to exclude 0 and 1 from the recurrence. Because, for example, when n is 0, log of 0 is, it's like dividing by 0, right? Can't do it. Log of 1 is 0. So here, even if I restricted it to 1, here I'd have a 0, and I can't ever pick A big enough to dominate those cases. So what I do is I just say, look, those aren't part of my, I just absorb whatever the cost is into the theta n for technical convenience, and that lets me address it as A n log n to be big enough to handle the base case. Okay? So that's why we made that technical assumption. Okay. We're going to use a fact, okay, which is that the summation of k equals 2 to n minus 1 of k log k is less than or equal to 1/2 n squared log n minus 1/8 n squared. And I'll leave that as an exercise for you to work out. I think it's an exercise in the book too. Okay? So I want you to go and evaluate this. There are two ways to evaluate it. One is by using purely summations and facts about summations, by splitting the summation into two pieces and reconstituting it to prove this bound. The other way is to use the integral method, okay, for solving summations. Okay? So either way you can prove. The integral method actually gives you a tighter bound than this. Okay? But you can okay? So this is a basic fact. You should go off and know how to do that. So now let's do substitution. So the expectation of T of n is less than or equal to 2 over n, okay, times the summation k equals 2 to n minus 1 of, now we do the substitution of a k log k, the smaller values. Plus theta n. I might mention, by the way, that the hard part of doing this, it's easy to get the bound without this term. Okay, it's easy to get this bound, 1/2 n squared log n. Okay, it's harder to get the second order term. Turns out you need the second order term in order to do what we're going to do. Okay, you have to be able to subtract a quadratic amount from the n squared log n in order to make this proof work. And that's the trickier part in evaluating that summation. So we get this. So that's less than or equal to, well, I happen to know how much this is by using that formula. Okay, so I use my fact. I get 2a over n times 1/2 n log n minus 1/8 n squared plus theta n. Okay, just by doing, did I do something wrong? Plus n squared log n. There we go. Very good. Okay, n squared log n. Okay. So that's equal to, if I multiply this first part through, that's a n log n. N squared log n. Sorry, a n log n. This time it is n log n. Good. A n log n. And now, so I don't make a mistake, I want to express this as my I'm expressing this as my desired, this is what I want it to be, minus a residual. Okay? So I'm going to write the residual as this part. Okay? And so the way to write that is that's going to be minus, and then it's going to be this term here, which is going to be a n over 4 minus theta n. Okay? And that's going to be less than or equal to a n log n if this part is positive. And I can make that part positive by picking a big enough such that a n over 4 dominates the constant in the theta n here. Whatever the constant is here, I can find an a that's big enough so that this term makes this part positive. Okay? If a is big enough so that a n over 4 dominates theta n. And so the running time of randomized quicksort is order n log n. That's what we just proved. The expected running time is order n log n. Now, in practice, quicksort is a great algorithm. Okay? It's typically 3 or more times faster than merge sort. Okay, so it doesn't give you the strong guarantee necessary of merge sort in being worst case n log n, but in practice, okay, if you use randomized quicksort, it's generally, as much as 3 times faster. It does require code tuning in order to get it up to be that fast. You do have to go and coarsen the base cases, okay, so that and do some other tricks there. But most good sorting algorithms that you'll find are based on quicksort. It also, one of the other reasons it works well is because it tends to work well with caches and virtual memory. So we're not really talking much about caching models and so forth. Big topic these days in algorithms. But it does work very well with caches in virtual memory. So it's another reason that this is a good algorithm to use. Okay? Good. So, good recitation, by the way, on Friday. We're going to see another n log n time algorithm, a very important one in recitation on Friday.